The Micro GC has two modules in it, or two channels in it. One channel has a molecular sieve, the other has a pour plaque cube, the one that you have. Each one of those channels has an injector. Each one of those has its own column, obviously the two columns I just named, and each one has its own TCD detector. So what we do is we take the sample and it splits and it runs in both of them in parallel, and then we take that information and then we just do an external standard and say that, okay, based on what our external standard is, here's how much of this product is in this unknown gas that we're going to run. The way that it'll come out, the elution order, and I suppose you have argon carrier and helium.
Yes.
Yeah. Right. The reason that we do that is because the thermal conductivity for helium and hydrogen are identical, relatively close to being identical. So you're going to get the same response. If you run helium as a reference gas through a TCD, you won't see anything. Actually, you will for hydrogen. It's kind of an interesting compound. It'll go positive for a little bit, and then it'll go negative. This causes a problem because you never know where the start of the peak is, and everybody's a little hazy on where that crossover point is. I like to think that if you're doing anything lower than 2%, you can probably do it on helium. If you're doing anything above 10%, you could probably do it on helium by inverting the signal. But there's that area, well, maybe 20%. So there's that area in between that it's just an upset baseline. So we run argon because there's great thermal conductivity between argon and helium, and we invert the signal and we get a really nice little sharp peak. What that does for you, though, is it reduces the sensitivity for some of the other compounds. Not that it's going to affect you guys, because the thermal conductivity is relatively close on argon and CO. So instead of seeing like we normally can on helium, we can see about 10 parts per million of CO. With the argon carrier, we'd be lucky to get about 200 parts. Again, well below what you want to see. So the elution order on a mole sieve is going to be hydrogen. Then we're going to see oxygen and nitrogen. And then we'll see either CO or methane. They'll be kind of close together depending on how well that column is separating them or what temperature we run. You can heat it and drive CO in front of the methane, but I like to leave it cool enough so that we can see the methane before we see the CO. CO is kind of an odd little peak in that it has a little bit of a tail to it, and if it's in front of methane, sometimes we can't get a good separation. Now, after that, we're going to back flush it. So the main thing that affects a mole sieve adversely is going to be water. Doesn't like water. Syngas generally has water. It also doesn't like CO2. And the two have two different effects on a mole sieve. One is, on a mole sieve, the elution will start, all of the peaks will start shifting forward. That means it's wet. If you start losing sensitivity on everything, that's CO2, and that's harder to get rid of. The main thing we want to do is make sure we get CO2 off of that, keep it off of that, which shouldn't be hard to do at 10%. The other column is specifically, because it's got a little pre-column on there, and we hold up the CO2 just briefly, and then we back flush it to vent. On the pour plaque cube, we'll get a composite peak that'll be all of this stuff, except for the methane, which will be separated a little bit. Then we'll get CO2, ethane, ethylene, ethane, if you separate those two, and then you'll get propane, propylene, propane. In between here, you might get a little water peak. So these are the C3s, these are the C2s, this is CO2, and this is C1, or CH4. Okay, so that's the basic principle is you're doing these.
One more time, because
Sure.
none of us are chemists.
All right,
So,
well, that's okay.
Yeah,
Because you don't have to be a chemist, you have to know what the elution order is, and I'm sorry, let me turn that off.
this is super important for us to understand.
Yeah, I mean, it'll be named and they'll be done by retention time, but this should always hold true because the retention time is going to be set by whatever we set the pressure to be on the column. So we're going to see helium, we're going to see hydrogen, oxygen, nitrogen, then methane and CO. On this other peak, on this other one, we're going to see an air peak, what we're going to call an air peak or a composite peak, that we won't analyze. We probably won't analyze methane, we'll probably do it on the other one. And then we'll start at CO2, C2s, C3s. If there's water, it'll be right in between the two of them.
And this
Water
is-
is a distinctive peak.
This is for the PPQ.
This is a mole sieve.
What's that?
Yeah. I
This
should
is
have
for
known.
the molecular sieve.
Mole sieve 5A, and this is a porous polymer cube. So that's the basic principle of it. Another thing you need to remember about the Micro GC, don't put water on it, don't put any liquids in it, don't put any particulate matter in it. There are actually two filters on this system. One of them you can see that's on the outside when Bert set it up, which is right here. It's a little 5-micron frit that's exchangeable. So if you see that you're not getting sample in, you might want to check that frit and see if there's anything on it. The other is there's another exact match for that frit, the 5-micron frit, inside this fitting. Don't ever get anything in there because you got to replace this fitting. That's why we have the external filter on it. So that's it in a nutshell.
It looks like it may be, we're going to do a more detailed training after the video session.
Okay.
For the video
Sure.
session, I would suggest maybe we can do walk us through the process, building the process, the method.
Method process? Got
Method
it.
building, and then run the method building and run the data analysis.
Okay.
We use air for.
That's what we'll do. We'll run air right now.
Yes.
Okay, so to build a method, the first thing that we need to do is running on experience, which is what I'm going to do. I'm going to guess at what these are. The things that we need to set are going to be the pressure, the temperature, and the length of the run. So the first thing is I'm going to take this little cool down method that we have and save it as something completely different. Let me see if you got one out here first. You have a couple? Is this an air sample method?
I think that's the one, yes, David help us.
Yeah,
We can start
Bert
from
did that
scratch.
one, I think. Pardon?
Do one from the scratch.
Oh, well.
Probably the easiest.
Well, it's always just as easy to, I don't think you'll ever have to do a new one, but if you did, you can. It's going to pop up with the same things that are in this cool down. So let's go from the very beginning.
Okay.
Let's back all the way out. We don't care about these.
Right.
So we start from scratch. First thing is we click on this Easy Chrome. And it always opens up with the last thing that you did. I don't like this little screen to pop up, so I'll turn it off and you won't see it again. This is a wizard for creating a sequence, a wizard for creating a method, doing a single run or running a sequence. But there's 4 or 5 ways to get to everything in the software. One is through the File menu, where you can open up a method. You can open it up in different areas. You can save methods if you go through here. You can save it there, or you can do a pull down on this icon and save it. I have a tendency to mix up the two, so I'll just do it the way I normally would do, and you can understand that there's more than one way to get there. The first thing we'll do is to tell this instrument what temperature it needs to run at and what pressure it needs to run at, because we need to start getting the temperature up to a level that we can work with. So the first thing I'm going to do is go and do a new method. You shouldn't have to do this very often. And on this new method, I'm going to tell it that the molecular sieve column, I want to run at 70 degrees. And I want the inject time to be 40 milliseconds. Something we didn't talk about was what that means and why it's reproducible. There's 2 constants that make a reproducible injection. One is, and both of them are set in the software. One is the column pressure. The other is the inject time, and I'll tell you why those 2 combine to make a reproducible injection. My mouse is stuck. Let's open this up a bit. My backflush time, just from my experience, I'm going to set at 8 seconds, because that way it should be cool enough so it won't allow the CO2 to come onto the mole sieve column. We might lose, at this low temperature, we might lose some of the CO, but we'll only have to play with that to find out for sure.
And you are targeting the air analysis.
Air analysis, but I'm going to try to get them all in one. I want to get everything. I want to get hydrogen, oxygen, nitrogen, CO, and methane. So if we can find some methane, we can find out whether this is going to work or not. There's no reason to have multiple methods because the whole idea is to separate out the compounds and be able to tell based on that what the concentrations are. The detector is on. That just tells me that the filaments are on in the thermal conductivity detector. The TCD limit check is on. All that tells me is that if I shoot a big, huge sample in and it's going over range, it reduces the range to half so that you don't get a big electrical or a temperature shock onto your filament for the TCD. We're going to invert the signal on this one because we're running argon. And if I don't, then all my peaks will be pointing down. I'm going to run in static pressure, and I'm going to put it at 22 psi. This never needs to be messed with as far as the acquisition channel. I always run a sampling frequency of 100 hertz. I don't know why anybody would ever want to not do that, so I really don't ever change it. The runtime, I'm going to say at 2 minutes, at 120 seconds for now, just so I can see everything. It won't be, well, we've only got air, let's just do 60. There's no reason that it'll get everything off in 60 seconds. So that's our first channel, and that's, down here it tells you that this is the one that's running argon, and it is the mole sieve 5A, which is a molecular sieve. The next part, the other channel. It's a pour plot Q. I'm going to run it a little bit hotter at 80 degrees. Again, my inject time I'm going to put at about 40 milliseconds because we should be able to see the atmospheric CO2 when we run this. Detector's on. Detector limit check is on. I'll run pressure of about 18 psi. Acquisition the same, 60-second run so that it matches the other. And that section is built for that particular part of it. At this point, I'm going to save this. File, method, save. And I'm going to save it as the analytical method so that you'll know which one to use in the future. Now I'm going to download this method into that analyzer. The reason I want to do that is because I want to go ahead and start the columns raising up. The thing about chromatography, it doesn't like being turned off. Any chromatograph doesn't like being turned off. You're better off leaving it run all the time. You're going to use maybe 15 mils of gas a minute, milliliters of gas. In that case, that thing ought to last a long, long time, like months. So just leave it running. It doesn't take that much power. Okay, so I saved it. I did two things there. First, I saved the method. I saved it in this method, saved it that way. But I also did something else that's pretty important, and that is that I went to the control section. Everything that's happening on that analyzer right now can be seen through this control section. If I'm going to make an injection, if I'm going to download a method, if I want to check and see what everything is, that's where I go to look at it. So I downloaded the method. When I downloaded the method, it started bringing the temperatures up.
Oh.
And I know this because I can go to the instrument status and look at it, and now my temp is 70 and we're coming up to it. My temperature is 80 and we're coming up to it. We've already hit the pressure points I need. At the end of this time, it's going to come, everything will turn green and it'll be ready to make an injection.
In other words, when
Go ahead.
After you download the method,
Mm-hmm.
that means you literally are running, preparing it.
You're preparing it. You're bringing it up to temperature. You're not running.
Okay.
But you shouldn't need to run all the time. You don't need to download it and tell it to run a sample. You just need to tell it what temperature it needs to be at so that it'll be ready when I want to make an injection.
Okay.
So I'm bringing it up. Now, the common parts, there's another thing that we control through this called the sampling time. The sample time is in seconds, and it's how long the little suction pump inside that analyzer is going to run. And I'm going to do it for 15. And stabilizing time is in seconds as well. That means once I hit a ready state, I'm going to stabilize for about 5 seconds before I let you make an injection. That was all under the tab Agilent 490 Micro GC in the method and the instrument setup. Baseline check, don't ever work with that. I usually remove this. It's just so that you can start a run and monitor the baseline for a certain period of time. If you just want to see if things are jumping around, maybe there's a pressure problem on the analyzer, and you notice peaks that are coming in that you don't think are real peaks, just monitor the baseline and see what it does for a while. Trigger is important. This will never run unless it is in none. The only reason well, that's not exactly true. Did you have a stream selector valve that you wanted to put on here? No, for some reason I was thinking there was. A stream selector valve will send a signal out telling that micro GC to run. So if you have a number of different lines and you're switching between them, it'll switch over to one line, wait, send an external signal out. Other than that, none. That way when we hit go here, that makes that analyzer work.
Okay.
Right?
So we were wondering because right now the sample injection here
Yes?
is done manually because we don't connect it to the gasifier yet. So
You have a gasifier?
Yes. The gasifier is not the one you define as gasifier from Agilent.
Okay.
And our gasifier generates CO and hydrogen. It's not the vapor.
Oh, your gasifier in your process. I'm sorry.
But basically,
Okay.
this is not completely the same thing at this moment.
Mm.
So we want to, the first attempt we want is to use a syringe and then inject that sample.
Well, if we're going to do air, why don't we just run the pump and
That's
pull
okay.
it out of the air?
That's okay. Yeah, that's okay. But that's the reason we have a trigger built in that.
You'd never, even then, you wouldn't want that
Okay.
because you just make your injection and while I'd still probably run the pump even though you're doing a syringe injection. How are you going to do a syringe injection on this? I need to understand that a little later as well.
We don't know.
Yeah.
And that Bert told us a little bit.
Okay.
Just to kind of try it.
Yeah, Bert's really good at that, and Bert's a good
Sorry,
service engineer.
Go ahead with your
Sure.
go ahead with your air
Okay.
analysis, and then we'll.
So what I've done so far is I've told it, okay, I want to run this system at this temperature. That's all I've really done. And at this point, I don't need that open. I can minimize this. And I'm just looking to see, I'm at temperature and I'm ready to go, so let's run a sample. Running a sample is pretty easy. I go with icons when it comes to this because this little go icon, for some reason, didn't want to have its name. That's a single run. Okay? If I click it, I'm going to tell it that I actually want this is an air sample. I'll put an underscore. There are things that you can put on here, like date and time,
Okay.
and an increment number. I usually put underscores on them because all the numbers run together if you don't. So I'll put an underscore and I'll put also a date and time.
I like that.
Yeah, so we'll do probably the same thing here, and you did almost the same thing I did. The ID would be air and whatever this increment number happens to be, but not the date and time. That's the sample ID, but on the data file I want this date and time as well. So I'm going to put an underscore and the date and time, because I like to date my data files. Also, this is the default. It goes into a default subdirectory called data, but you can also put it into one for the date. So let's put one for today.
Okay.
All right. So we put a slash in there, and I usually do my dates like 2001 underscore 8 underscore what is 31st, 30th, 30th. This is ready to make an injection at this point. Let's go ahead just for the fun of it and say we want to do 5 of these injections instead of just 1.
Okay.
So you can do replicates this way. So if you're going to run the same gas over and over again, you could do replicates this way and you can track it by the time. So maybe that's a good way to look at it. This is also the screen we'll use whenever we calibrate, but we'll get to that later. So we say start. Okay, that folder doesn't exist, so I want to create it. Current method has changed. Would you like to save it? Thank you for telling me that. Yes, I do want to save it. And then we should be able to look at these 2 channels of data. Where's my other one? The suction pump kicking in. at the end of that, it made the injection. And it's putting both of these on one run, on one screen, which I don't like very much. I'll break this up and put them on two separate screens.
It's convenient for users. A non-chemist in the sense.
Okay, well, you can look at it that way. It's easy. I'll leave it the way you want it.
Yeah.
You can blow these up as they're coming off, and you can see that there's my one peak. And I need to take a look inside this box. Because I think that you have argon running to the wrong modules. Yeah. Should be running to the mole sieve. I think it's running to the pour plot queue. There's no reason that these should be negative. I inverted the signal on one channel on the mole sieve, so it should have been up. I'm going to stop this because I don't want to run this anymore. And you might want to stop at this point because I'm going to have to take that analyzer apart. So
maybe it's time to install the filter base.
we could do that, but we need to check that.
I recall that for Bird was you inverted one of the channels, the signal.
I did as well
Okay.
on this one. If you go into the instrument setup, you go and look at the method. I inverted the one on channel 1. Channel 1 is a mole sieve. The fact that I inverted it and it's now going negative means that it's got helium running on it.
Okay.
Which is it's not critical, it's not good. Because the TCD voltage is different when you're running argon or when you're running helium. If you're expecting to run helium, it sets it at 15 millivolts. And because we're running and if you're expecting to run argon, then it sets it at 10, so you lose sensitivity. I don't think we've hurt the analyzer at all, because if you go and look at that data file, even though it's inverted, we can go in here and look, and we see that the peaks are nice and pretty. The baseline is good. What we're looking at is oxygen and nitrogen on the one, and just a composite air peak on the other. I can blow this up. Don't know why he put both of these on one channel, but if we blow this up, you can even see that this is going to be CO2 at about 400 parts per million. So I know where the CO2 is coming out as well.
Mm-hmm.
So let's get that fixed,
Okay.
and otherwise I don't want to run any more samples.
Sure.
Okay.
No, that's fine.
We're getting old and fat. So a little more forceps than I used to. Okay, so this is my number 1 carrier, right? Coming through here. And it's coming through. It's coming through here. Going back into this guy. Doesn't make a lot of sense to me, but this would be the number 1 module, number 2 module. Number 1 carrier is going to this one. Number 2 go to this one. It was not an easy call for Bert. I mean, I would have thought the same thing. I've gotten to where lately I pull them apart.
Good idea. So again, argon, channel 1 is argon or helium?
Channel 1 should be argon.
Okay.
Right now, it's not.
Okay.
So if you've got a Sharpie, why don't we just mark it on the back of the end?
Okay.
This is good.
Okay. Now, I would recommend putting a valve on both of these
Okay.
so you can shut them off.
Okay.
There's a couple of reasons for that. Number 1, it's easy to flush these guys out because just by definition, the way this works, it's got that little dip tube in it, so it's got a little bit of air in it, so always flush it 2 or 3 times. It's not as important on yours, I don't think.
Yeah, well, actually, to tell you the truth, that I had a hard time to find a partner for the buyer. But
It
before
would be
you
under a
do
switch lock. Go to switch lock side, would be the easiest way. Switch lock makes one. A lot of people use.
Yeah, that's okay, but maybe before you go, we can get the phone number for you.
Yeah, a lot of people use maybe a little swedge lock like this guy. And some people use ones like this guy.
Okay.
Like, so that's a hook, I think. I gotta turn your gas off though. Got to disconnect everything. While I'm taking it apart and talking about it, the carrier gas ought to be set at 80 psi, plus or minus like 5%. I think the spec says plus or minus 10. I'd say plus or minus 5. And the reason is that it's also used to drive the solenoids, and so they have to be within a certain range. Okay, let me make sure of this. This.
So you, I'm not recording this. Oh, okay.
Shot some of these lines for a while.
Inside.
That's it. The other thing that we do, you'll notice, is we've actually had 2 pumps. And the reason we do that is sometimes if you pull an argon helium through 2 different channels, especially if you're doing hydrogen, because helium comes off exactly the same place as hydrogen. You want to make sure that none of it's back close and through the pump. So we fixed that a long time ago. This is operating really well, just from the way that the peak shapes and everything look. We just need to get it configured correctly. All goes back together. I have a tendency now to drop these little screws inside of the cabinet and then have to take it all apart again, so I don't want to do that anymore. How high up in the hydrocarbon range do you think you might have to go, Doctor?
Not very high.
Just the C3s, probably? That's good. Pour plot works really well for that, but if you wanted anything higher, I'd want to go with a different kind of column.
In the chemistry department, I have what is 490 model,
Mm-hmm. A 4900.
4900 is.
Yeah, this one's a 490. So they're familiar with running it then?
They are, and, I'm not. So I'm learning from scratch. I think I have a couple of Agilent products in the laboratory.
Okay.
This one will designate for syngas analysis.
All right. So we wait for it to come back to ready. First thing it's going to do is go through
Yeah, push the on the stand.
go through the that.
Push the yeah, just push that.
Push that.
Oh,
Okay. Goes through this Christmas tree lights while it's getting ready. At the end, it'll start flashing 2 green lights. That's when it's in a boot P. That's when we could go through and set the IP address on it, and then it'll come to ready.
So in the process, it will flash to the system.
First thing it does is goes through and does a flushing of the system, and in fact, we'll go and open up the software. We can tell what's going on the analyzer. So go to control. There it is. There's communication error. Oh, we got this communication error. I gotta clear it up first. That. Okay.
Probably didn't want us to talk to it while it was going through that initial startup. Should be. We'll take a look. Okay, so we go to the control, because anything we want to see on the analyzer we do through control. We go to the instrument status, and it says we have a communication error because we don't have a cable plugged in and we don't have Bluetooth yet. That would make it a lot easier. Now it should work. No matter how hard I try. I like simple, stupid mistakes because they're easy for me to fix.
What is it doing right now inside? It's making noise.
That's the solenoids that are going through their diagnostic clicks. It goes through a check of each one of the solenoids on all of the pneumatics. It also goes through a flushing state where it's opening them up and flushing all the gas out, which is good considering we've got the wrong gas going into it. We may have some little, there may be a few things that we see in the software or in the chromatogram right now that won't look normal. I won't know until I run it. But we'll take a look at it and see. So it tells you that it's in the flushing state. When it's doing that flushing, the detector is not on. That's a good thing because we turned it off because we had the wrong carrier gases running to the wrong systems. When we get through with this, we run it with no change in the method and it should look right. As far as your view, if you wanted an overlay, you can certainly leave it that way. But I'm going to do it in tile right now because I'm a creature of habit. And if I don't, I won't know what I'm doing. It's kind of easy to fix these things. I know that it seems like it's really busy, but whichever one is on top, towards you. So in this case, the pour plot is towards me. I can right-click and say tile horizontally, and I can see the 2 different channels. Again, we'll fix this, and we do see that we're getting our peaks out in time, and we're getting all of our peaks. This would have to run longer for to do methane and CO, which would come out here towards the end. But we've got acres of separation between oxygen and nitrogen, so I'm going to raise the temperature a bit. And I can do that while it's going through that flushing state, I think. Let's find out. So on the mole sieve, which is the one we were looking at, and it says at the top, I'm going to raise this to 90 degrees. And save the method. Save method. And download the method, and I think it's going to tell me it won't let me do it because it's in a flushing state. Maybe it did. Yeah, it's still flushing, so it didn't let it download.
Temperature, you will be able to narrow down the gap between nitrogen and oxygen. So,
Actually, what I'm going to do by increasing the temperature, I'm pushing all the peaks closer to the front. And that's going to have the effect of pushing together the oxygen and nitrogen. The theory of chromatography being that there's an affinity. In a mole sieve, it's not so much an affinity, but it's got 5 angstrom holes in a molecular sieve solid. And the gases go in and come out at a different rate. So hydrogen is almost unretained. It goes through very quickly, so it's the first one out. The next one is, of course, oxygen and then nitrogen. The things that affect how quickly it goes through that 10-meter capillary is temperature and pressure.
the higher the temperature, the more...
The faster. Faster it comes out. The higher the pressure, the faster it comes out. Pressure is, we use pressure because it's easier to control pressure accurately than it is to control flow, at least economically. So we set pressure, it's a constant pressure, we don't have to change the pressure, so it's always coming through at the same speed. And still going through that flushing step, probably because we had to switch the 2 carriers. And it wants to make sure it flushes it all out. This is a pretty good little diagnostic to look at. One thing to know when a detector is going bad is you'll see that the auto zero will start going very, very high, over 200 or 300 millivolt. We'll see what it is when it comes on. We can't read it until the detector goes to on, which takes a while when it's going through this flushing stage. Any questions right now would be a good time because there's nothing else going on.
When you're talking about the syringe,
Mm-hmm.
how, you're going to explain later on how we'll go about that process.
I'm wondering why you want to do a syringe. To me, a micro GC is a gas analyzer. By definition, you can't shoot anything but vapors in it. You'd have to have a gas-tight syringe with a valve on it. Most times gases are a little bit pressured, and if they're not, I've got a pump to pull it in. If you buy a standard, it's going to be under pressure, and you just need to make sure you never put more than 15 psi on it, hook it up, and with the suction pump and that positive pressure on the back, you get very nice reproducible results. I guess it's because of your sample and how much gas you're going to make. Usually people make a syringe injection when they're limited on how much sample they're going to have. So for a lot of bioreactors, a lot of people who are doing really low fermentation work, they only have 50 mils of gas or something like that, so they want to limit it, how much they got going in. And I don't know if that's going to be the case with you.
It will be. The faculty in biological science
Okay.
will become one of this afternoon.
Okay.
He's the one who does the fermentation.
Well, you didn't buy a syringe injection system. I mean, we do sell one. This is the standard setup that we do for most gases. We also have another one that would add a valve so that you could switch back between the two, and it has a pressure relief on the back of it, and then it has 2 little capillaries that come over, and you can inject them into the front of the analyzer, and we can either put a lure lock here or a septa. What Bert was talking about is putting a T in line, maybe, and doing a syringe injection, and I think he got you part numbers for that. There's a caution when you do that. What you need to do is make sure that you'd have a T. It's hard to, I can draw a picture, but you'd have a T coming in, and then a short capillary where you could put a septa on the end and inject into that. But you're going to have a valve, and you're going to have another valve, because you're going to have to isolate the two. And the one valve going into it from the sample that needs to be pulled or has pressure on it, the standard system, has to be very, very close to where that T is, because otherwise you're going to get part of that sample will always be there even when you're injecting and trying to go past it. It's if they have to do it, fine. It's not the way I would do it. I would go with especially some sort of a, depending on the type of flow you had or how much flow you had, you would should always have enough flow to get through this system of pressure.
In other words, inline connection is the best.
Absolutely. Even, or maybe even a Tedlar bag or something. I mean, if they're limited on samples, there's pretty small Tedlar bags, not real small, like 100 mil or so, or 200 mil, I think they are. I'll talk to them about it when they're here.
Okay. That's the thing I think we need at least. For us, the quantity of gas is not a problem.
No.
For them, it's a problem. So we probably need what do you call this bag?
Tedlar bag. How big, when we're talking about limited sample, how big a sample are we talking about? Do you know? Mm-hmm. Well, I'm thinking on the bio, if anybody knows, fermentation process. Don't know? For yours on the gasifier, you won't ever use it. There won't be a liquid injection. I mean, there won't be a syringe injection.
From biological fermentation application, we want to use meal scale, maybe 10 mil.
10 mil is going to be very hard to do. I mean, you think about the thing that you need to, the loop on the injector is very small. It's 1 mil. Actually, I think it's smaller than that. I can't remember my numbers right now. But there's all the tubing that's upstream of it.
Yeah.
And what you want to do is overfill that loop about at least 5 times. Well, there's your 10 mils gone quickly. And I've got a person doing just that, trying to do it with 10 mils out in California right now, and she's not getting reproducibility at all. Now, I think she may be doing something wrong, which is why I've got to go out to California in a couple of weeks. But I have a person at the USDA who has the configuration with the syringe injection like a SEPTA in the front. On his system, I'm using about 5 mils of gas every time I do it on a gas-tight syringe. But again, he's got very tiny capillaries coming from here up into the back and through a pressure pop-off that goes into it and into the injectors. This still says it's flushing, which may be because we took all the pressure off of it. I'm going to reboot just to see if it's really flushing or if it hit a diagnostic step. Should have a communication error. It's going to give me a little break. Instrument is in the flush cycle. Yeah, okay, not anymore. I just turned it off.
The bag what's the name of the bag?
It's a Tedlar bag, but if you're saying that they're limited to like 10 mils, that's going to be too big.
For us,
Not for you.
our application,
Mm.
I think we use it.
There are a number of different bags you can buy. If you just go and search under, if you Google air sampling bags, I can't remember the name of a company right now. It seems like one's called Gas Tech, but you should be able to search it pretty easily. And it has a little valve on it where you can push gas in, where you can fill it up slowly. And then you could just take a piece of Tygon tubing on the back of this. I may have some with me. I keep some with me in case I'm ever doing that type of work. And I'll put it on the end of that 16th-inch fitting. This one's kind of dirty. And the other one would go onto that Tedlar bag. You open up the Tedlar bag and hit suck and keep a little bit of pressure on it and it'll pull it right in.
Yeah, some people call it balloon, and so it's 4 years of balloon.
A balloon.
Yeah.
Yeah, balloons are a little permeable. The nice thing about the gas bags is that I think they're made out of like a nylon material, and
Okay.
they don't let anything through. Let me see if I can talk to this guy again. Click that one. Yeah. Okay. Right, easy chrome software.
I think it's going to tell me it's got to double click it. Should be opening. It's flushing again, of course, because I just told it to. Any other questions while we're waiting? Analyzer likes to be sure it goes through its diagnostics. Every time you restart it, it goes to this default setting, which is 30 degrees and 7 psi, which is annoying because if you have a method set with 150 degrees temperature on it, all you did was turn the power off and back on, and it's going to go down to this, go through a flushing step, and all your temperatures are going to drop off, and you got to wait for it to come back up. I'll look at something here. Yeah, me too. That's one reason why you have such pretty and big and peaks here. You'd know it the first time you tried to run hydrogen on it, because there wouldn't be any. You wouldn't be able to see it. That's probably a little bit of helium that was there from the other line. I'm surprised we don't see some argon right in this area. The software is actually pretty easy to use. It's all on one screen. There's not a lot of clutter. All right, where are we? Still flushing. There's a little bit. It's pretty well documented in the manual, but you'd have to read the 170-page manual, which is not so fun. I was with Varian, but not when the acquisition happened. I was with Varian. I started with Varian in 1988, and worked for them in the inside sales group and in tech support, and then became the product specialist for the Micro GC when we bought ChromePack. So I know the previous version of this and the 4900. I had left and gone to ABB, which is more of an engineering firm, and was there for about 5 years just before they realized that when they kept this analyzer, which was an analyzer from Varian, that they didn't keep anybody from Varian who knew anything about it. Not in the U.S. anyway, certainly at the factory. So they We're looking for product specialists and some application engineers, and asked if I would come back and work on it.
Yeah, I noticed that also. I don't know when the acquisition happens.
It actually happened in November of last year is when it was finalized. It's when they actually folded the two together. But they've been working on it for about a year before that. So, and then they divested themselves of the Varian GC line, the benchtop GC line, and sold that off to Bruker. But they kept the Varian Micro GC. Okay. That's the reason they didn't know anybody about it. I didn't know anything about it. It shows it's ready, but it still shows it's flushing, so I'm not quite sure why it thinks it's in that flush cycle. I want to see if there's when I turned it off, I might have left something running in the processes that I actually needed to shut down. Got all those service hosts open. My services are all open up on it. I think probably what we'll need to do is... Pardon? Yeah, the ready light came on, then it went off. There we go. It just came up.
This was...
Yeah, and it's not now because it's trying to reach the temperatures. And as soon as we get back up there, we'll run another one. Again, a number of different ways to do it. You can either do it from control, single run. It gives you the icon so that you know which one you use. Or use the icon. So I'm going to run the icon again. They haven't gotten any less expensive now. The real savings in the micro GC is not so much. The engineering is still the same. The electronics and in fact, it costs more to make the injectors. So that's one of the things. The real savings is the amount of gas that you don't use, and the speed of analysis. Because on a benchtop system, to do this same analysis, the fastest I could do it would be somewhere around maybe 12 minutes on a standard gas chromatograph. So we gain a lot in speed and productivity. Mm-hmm. So hopefully this time the peaks will go in the right direction. The two pumps kick on. It's pulling a sample, in this case just air. I'm sorry?
You increase the temperature.
Yes, I did. So they should be a little bit closer to the front. Not a lot. We only changed it, I think, about 20 degrees. One thing you'll notice is this shift in the baseline. This is normal. What's happening is the way that the system operates is there's a reference gas, which is going through one side of the thermal conductivity detector, and then an analytical. And it's always measuring that reference, giving you a constant current. And the other one, whenever another compound comes through, it has a different thermal conductivity, and it gives you a signal. Since they're matched at the beginning, Once we do a back flush, the way it does a back flush is some of the flow goes away to back flush the sample to a vent. When it does that, it shifts a little bit from what the other reference signal would be, so there's a little offset. It's just a little bit of an offset. And that's more like it. So now, I forgot I set this up to run 5 of them. There's really not any reason to. Let's just stop. I'll change that so that the next time I do it, I don't start 5 runs. I'll put it back to 1. So I'll open up a file. Oops, sorry. Data file. I'll open that last one that I ran. It says it's running. I told you not to run. Stop all of them. Thank you. I'll open up that data file that we just ran, which is the last one in time. And now I can start identifying the peaks and telling it what the integration parameters are of the chromatogram. This is good enough for what we're going to be doing and good enough for the work that you're going to be doing in the future. Again, we see the CO2, which is the atmospheric CO2, at about 400 parts per million. This other peak out here is water in the air. I'll save this method. I could probably heat this one up as well, and I may do that. The propane products would come out after that, and what I may want to do is go ahead and make it longer so when you run a propane we'll be able to see it. So since I know what the elution order is, and I know that that's water because that's what water looks like on a chromatogram, it's a big tailing peak. I'm going to go and change the method in the instrument setup, and I'm going to run it for 90 seconds as opposed to 60. I'm going to save that method, and I'm going to download that to the analyzer. But that doesn't stop me from doing this. Well, we'll do one so that it's got the right end time on it, and I'll show you some of the things that we do as far as the integration events. So we're going to run another one, just like the other one, only this one's going to be 90 seconds long. At the end of that, then I'll go through and set the integration events. The software was developed originally to run micro GCs. The Scientific Software Incorporated was the name of SSI. Then the guy who wrote it, who happened to work for MTI, which was the first micro GC out there, split off, and he said, you know, it's fine. I'd like to take my software with me when I go. And so he kept his software and started developing it, and it became a client-server type full-blown chromatography data system so that you could hook up 200 different analyzers and 15 different servers and pull it all in and access it from anywhere. Because it's like that, the base software itself has these parameters set in it that don't match up to micro GC anymore. And one of those is, in chromatography, how do you define a peak? That's always important in any chromatography software. And the way you define a peak is you establish whatever baseline is, whatever your regular threshold is. And it's set in picoamps usually. And my baseline's gonna fluctuate this much. Okay, that's my threshold. So I want my threshold to be higher than that, otherwise it would just see a whole lot of trash. Then, when it comes off of that, if my baseline starts to move up from that, that could be the start of a peak, or it could just be the baseline drifting up. So the second parameter we have to set would be how wide the peak is, how wide we expect a peak to be. If it comes down within that certain amount of time, that's a peak, and I can now integrate from front to back. Otherwise, it's just a baseline drifting up. So the two things you have to set are the threshold and the peak width. Well, the threshold and peak width on this is set for no chromatography that I know of, because it's set at 0.2 minutes. 0.2 minutes, which is 12 seconds. there's no peak ever on a micro GC that's 12 seconds wide. The whole chromatogram is 90 seconds wide. So we have to change a few things. In the method, the instrument setup was the first thing we did. So the most obvious next thing we have to do are the integration events on the chromatography itself. What I'm going to do, because this is method development, is I'm going to say, I know that this is not going to see a peak until about out here because this might be a little bit of helium there. And that means that hydrogen is going to come out somewhere in that area. So I don't even want to look at anything up to 0.35 seconds. Let's fix the peak width first. Instead of 0.2, instead of 2 seconds, 12 seconds, let's make it 1.2 seconds. That's how quickly the peak would have to start coming down for me to say that it's peak. 0.02. And threshold I can set graphically. But the first thing I want to do is tell it I don't want to look at this stuff in the front of it. I want to turn the integration off from 0 to 0.35, because that's about right here. And I'll say save the method. And I can analyze it and see that it doesn't even start looking for anything till about there. The next thing I want to do is set my threshold, and this can be done graphically. In this case, I'm going to. I want to say I want to set the threshold. The threshold of a baseline should be about whatever that threshold is, and it tells me that it's 337. The software will calculate it for me. Well, I like to go a little overboard on it, so I'm not going to make 337. I'm going to put 1,000 in there. Then I'm going to analyze again. And sure enough, it still finds some peaks there that I don't want it to see. So 1,000 is not good enough for what I want to do. I want to put 2,000. Say analyze.
Baseline is here, right?
Right. I was just finding a flat spot.
Okay. And how do you relate this to 2,000 or 1,000? This is 1,000 milli or micro?
I think it's picoamps, but I'm really not sure. It comes up, and the one that shipped as the default is 50. 50 is obviously wrong. 10,000 is too high because it's taken off some of the peak that I think is here. And by the way, this baseline looking like this is because we had the wrong air carrier gas going on. This is we'll bake it out again overnight tonight, but we'll make this look a lot better. So I'm thinking maybe I'll split that 5,000. This is just experimental until I get it to where it's drawing my peaks about where I want them to be. And it seems like it's kind of drawing them there now, although it's finding a bunch of junk in there that should not be there. Full unzoom. This stuff up in here shouldn't even be there. And a lot of that has to do with, we'll probably need to flush it 3 or 4 more times. I'll do that before I leave here today. Okay, so that pretty much defines the peaks that I want to know, which is oxygen and nitrogen. That's all I can really look at on this channel. Once I have these things set as far as my threshold, my integration off, so it's ignoring anything up to here, till I can see maybe a hydrogen, which I'll have to shoot later. Then I can tell it what these 2 peaks are because I know that. And what I'll do is I want to add multiple peaks to the peak table also. This is graphics down on the bottom. And you can put your cursor over it and it kind of defines it for you. You can put 1 peak or multiple peaks. Or I could go to the next part of the method and I could type them in. I like to do them the other way. And the reason I do is because it also puts in what window you should expect based on the width of the peak. So if I go to define the peaks, okay, I want to define the peaks between here and here. Just on the front and back of those 2 peaks. And it dropped those into my peak table with their times on it. It doesn't know what those peaks are. It just says, here's 2 peaks. Name them. The first one is oxygen. And the second one is nitrogen. analyze again. And something I forgot to do earlier, I'll go to the annotations, and I want to put the name of the peak and the retention time of the peak, and say, and apply it to all channels, and say OK. So now it says, well, there's a bunch of other stuff on here that you didn't name. Like this is a peak. We don't know what the name of it is. It's really not. It's a bunch of stuff on the baseline. But this is oxygen, and this is nitrogen. I'll do the same thing for the other channel. The thing to remember at that point, though, is that there are integration events for each individual channel. And the one that I was working on was channel 1. Channel 1. I got to change this now to channel 2. And if I went and looked, I would see that the integration events are the defaults again, which I don't like. So let's minimize that guy so we can get the right one up here. Okay, so now I have this chromatogram that I'm working on. And I can analyze it. Sure enough, that didn't do a lot of good. But it does kind of define my peaks a little bit. And I think it's because it also has a noisy baseline based on the changes that we made. That's pretty good, though. Now, in this case, I don't want to even calculate that peak. It's the air peak, but I don't care because I actually have the components of it broken apart on the other channel. So I want to ignore any integration up to the time when maybe methane would come out, which would be about here, but certainly CO2. So we're going to put it out here at 0.5. We're going to say don't look at anything up to 0.5. I can click on this cell. There's a pull down. One of them is called integration off. I have to give a start time of 0. I have to tell it when it's going to end. Well, it's going to end at 0.5, 0.5. And I analyze, this little analyze button. Sure enough, it ignores that peak.
So it's called integration off.
Integration off. Now I have 2 peaks here. I'm probably going to go ahead and tell it that that's water so that it'll know that that's a water peak. So I want to add my peaks again. Right-click here. Or I don't right-click, but I click this icon. It says, where do you want to start looking for peaks? I want to start there. Where do you want to end looking for peaks? I want to stop there. OK. Now if I go and look at my peaks and groups, I have 2 peaks named. The first one is, I'm just going to put CO2 as an abbreviation, and the other is water. Now if I analyze again, it puts their names there as well. Okay, and that's as much chromatography as I can do on air. There's not enough out there for me to see anything else. I can't see the CO2 that's in air because it's far too small. And we've got to let that cook out a little bit. The next thing that you'd normally do on a system would be to calibrate these peaks. But we can't really calibrate the peaks because we don't know how much there is. And we can guess that there's somewhere between 360 and 400 parts per million of CO2 in the air. I think it was 320 when I was growing up. It was down around 300. I know it was 320 or 340 when I started in chromatography. And now it's up to about 400. We certainly don't know how much water is in the air, so we can't quantitate that peak. We'll just name it, but we won't ever say how much is there. On the oxygen and nitrogen, we can kind of do those. We know what the mixture is there. So if we go back over to the mole sieve, and we call up that chromatogram. Well, let's just close a bunch of this because it's kind of busy. We can save this method that we've added those peaks to, by the way. But if we go to, that's not it, this channel, I can kind of calculate these pretty close. I mean, close enough for plus or minus 5% probably. If I go to the peaks and groups, minimize this a little bit, open this guy up. Not quite so much. I got to go over and tell it what level it is. And it's got a lot of busy things here that you're not going to need. The thing you need to remember is that you're going to have to work with levels. And the level of oxygen that's in here is about 22. Let's go 22.0. And the amount of nitrogen that's in there is 78.0. And we'll say File, Save Method. Now I can calibrate the system, and it will tell me that the next time I run one, it'll calculate what this is. So I want to go in next to where Analyze is up here. Right? There's an icon called Single Analysis Calibration. This is all here, by the way, in Analyze and Analysis Single Calibration. I just run on icons. So I go to this guy, and it says, okay, which data file do we want to use? And I'm going to use the one that's open right here, this air. And I'm going to calibrate. And I'm going to calibrate my first level. And I could calibrate 1 through 10 because there's 10 different levels there. And I want to clear the calibration just for this level, because if I had other levels, I don't want to throw that stuff away, just only this one. And I'll say, okay, well, that's what I want to do. I want to start. And it now says that if there are this many area counts, that's 22% oxygen. And if there's this many area counts, there's 78% nitrogen. And I can look at a report on my external standard, because that's what we're doing, is an external standard. And it will tell me that I just calibrated this and that these area counts correspond to 22 and 78. So now I'm going to run an unknown. It's going to be an error. And it'll calculate based on this what it thinks is in the air. It should be pretty close. Let's find out.
First you generate the data file, then you do calibration?
Yes. You can do it all at the same time. I like to generate a data file because I like to look at it and say, okay, this looks pretty good. And a lot of times, too, if I'm doing a calibration of different calibration gases, I'll run 2 or 3, and if they're exactly on top of each other, I don't use all 3 and average them. They're all the same anyway. I just take the last one and say, this is my level, and I calibrate it. But you're going to have to get calibration gases for all the things you want to see. Another thing to talk about while this is running, because a lot of people get confused when they think about calibration. You're probably okay doing your calibration with 100% gases, because you don't. It's 1%, plus or minus kind of thing. Your calibration gases that you use should make sense. If I'm going to do the analyzer's specification is plus or minus 0.1%, right? So if I'm going to do a calibration of a particular compound, and I'm going to look at 100 parts per million, and the range that it might actually happen is 100 parts to 1%. Then if I do 100% as a gas and just draw it through 0, that might be accurate, but maybe not. This one should be fairly accurate, but not really accurate. If I wanted to do 1%, and this was my range, 100 to 1, I'd get a calibration gas that was probably about 10%. So I'd do 10, I'd force it through 0, and then I'd be looking at here, and that's a fairly straight line, and 1% would be valid, and even 100 ppm might be valid, pretty close. It'd be better if I had a 5%, and that's because what you're looking at is 5.000. Okay, well, my reproducibility is somewhere around here. That's 1,000. That's 100. So 10 ppm is my limit by doing external standard of what I could expect the analyzer to reproduce. So I don't want to get any better than this. I certainly couldn't use 100% because that would be, you know. Well, somewhere about here, which is 1,000 ppm, should be what I'd expect my detection limit to be. It reproduces to 0.1%, so about 1,000 ppm. So don't do 100% of something and expect to get decent numbers down in the ppm range.
The point is that the calibration gas should have a similar composition as the
To whatever you're going to look at. That's absolutely right. But higher.
higher.
It should have a similar composition to what you're going to look at its highest test range.
Okay.
Yeah. Because the other side of that equation is, okay, let's say that, okay, I know that I'm going to be looking at 100% or 100 ppm to 1%, so I'm going to make my top standard 1%. Well, in reality, that 1% is real, and anything else that it calculates out here is a guess. I mean, it's a valid guess. It's probably a pretty good guess, but it's a guess because you don't know for sure if it's still linear beyond that. Okay, so I go now and look at an external standard, and this calculated the area percent or the area counts under those two peaks. I'm assuming they're pretty close. In this case, it's telling me there's 21.7% and 77.1%. So it's not exact, but it's pretty close and it's in its range. The reproducibility when you're pulling a sample through that doesn't have any pressure on it is not as good as it would be if you had some pressure on it, either from a bag or flowing from your reactor. The important thing is never get above 15 psi because you'll blow the injectors up. So your upper limit is 15. The other thing to remember about the injector on the Micro GC is that when the sample when it's not sampling, it's deadheaded against the injector. And when I say against the injector, it's in this case it's a silica chip with a little, pressure point. So if you've got 42 pounds of pressure on your reactor, even if you're flowing 1 mil, doesn't make any difference. If it's sitting there, it's eventually going to come to 42 psi and it's going to blow a hole in that injector. So you have to keep it below 15. And I don't know if yours even has pressure. I don't know how the process itself.
No, not a very high.
Okay.
Actually, the gasifier was a little bit of vacuum, not very high vacuum,
A little bit of a vacuum.
Yeah, lower pressure.
That's doing partial pressures is really hard to get any kind of reproducibility on too, because the vacuum pump works the same, but if it's at 0.95 bar or atmosphere, and then it's 0.9 atmosphere, there's a different amount that it's pulling into the system. So your reproducibility may not be real good. You might like to try to get a little bit of positive pressure somehow. That might be another reason for a syringe injection, or for having the gas fill into a bag, like a Tedlar bag, and then maintain a little bit of pressure on it. Yeah. Any other questions? It has some the software has some built-in reports. This is one of them. This is the one I use probably the most in gas chromatography, which is an external standard calculation. And it's also saying that, okay, what was our reproducibility of one air to the next? The total was 98.9, so about 1% pulling a sample through. Better if I had pressure, that'd be 100. It'd be exactly 100. You can review each one of the calibration lines. We only have 1 point through 0, so they're both perfect. But it calculates what your response factor is for both of the two analytes. So when you run an unload, it applies that response factor to the area count. I can also output this results, and this may be of value to you, and I want to talk about it now, because I can take the data for each one of the peaks, and I can export it as well. So I could export the area, or I could export the external standard concentration. And this is for both the two, so this is only doing one. This is only doing the one for the mole sieve, so if I wanted the other one, I got to go to this guy, and I would say I wanted the area, and I wanted the external standard concentration. And I say, okay, save that method. And if I run another one, it'll only take a second. Let's do you have Excel on here?
I do not remember,
Maybe? We'll find out in a minute. If not, we can open it up in a text file so we can look at it. But I'm going to run 3 really quickly. And it will do, for each one of the ones that I chose, each one of the parameters I chose, it's going to create a file. And that file, oh, I didn't see where I put it. Let me look at something really quickly. Dadgummit. I didn't tell it where to put it. So, may not do it. In fact, I know it won't. And it didn't come up and tell me that either. I want to stop all the ones in the queue. As long as I wait a minute, those peaks are still coming out. Even though we don't see them, it doesn't make any difference. So it's still doing chromatography. I'm just not looking at it. So I got to take a little more than a minute to do this, but I got to go to my advanced reports and tell it the path that I want this to go into. And I'm going to create one on your computer on C. But I'm going to go to C and create a subdirectory called results, or micro GC results. Right. Now, save it. Doesn't exist, create it. Yes, please do. I'm going to tell it the same thing in the other channel. I did this the other day and had 2 L's in results, so I want to check it real quick. Now then, I want to run a sample again. Again, I'll run 3. Now we'll go and create those files. What else do I need to show you guys? I guess, are you going to be running... I don't think there's any reason without having it automated or having a gas coming to it to run a sequence. If you can figure out a way to come from your gasifier into the analyzer and then automatically sample it every so often, then I would build a sequence. But there's really no reason to if you're only running one gas at a time. You can just name it each time, and it keeps the defaults in, as you can see from what we did before.
But the repeated test is good. And once we get a balloon, for example, and then we will be able to run
Right.
5 times and just, so we can throw probably the first couple runs out.
But even in that case, if you wanted to run 5 runs, set it to 5 running the same, you can set replicates and it just runs 5.
That's what I'm talking
Yeah,
about.
there's no reason not to.
So, and show the difference between the first one because of the tuning here, because the field is
Yeah.
there.
I think probably more importantly is that the reason we've had such ugly baselines right now is because the pneumatics compartments were filled with the wrong carrier. So they're also, they don't flush, they flush as well as they can, but there may be obviously there was a little bit of hydrogen in there, or helium in there. It seems to be going away now, so now those aren't nearly as notable as they were before. This guy still got that water out there. So the humidity is fairly reproducible in the room, but we have no water. Gas chromatography is not a really good way to do water. Why? Hard to get a water standard. It's very, very hard to get a water that you know is reproducible in a gas. Because even a change of 2 or 3 degrees temperature means now it plates out and it dews out. It's the vapor pressure is just not high enough to keep it in a gas. just to show you that it actually did it, if we go to this guy, and we go to the local disk, and we go to Micro DC results. Where did I put that? I thought I put it under C. Oh, there it is. Sorry. Couldn't see it. That line was just on it. It created a file for each one of these four parameters. I don't want to open them right now because if I do, it won't write to it. So don't open it while it's running. Otherwise, it can't write to that file. But we'll go look at them in just a minute. We're already on our second analysis. Oh, sorry. Any questions? Anything that's not clear?
When you're looking at the peaks, how are you sure of what exactly you're looking at? I mean, when you're saying this part is hydrogen or this part?
That was because I saw a little bit of helium that was there from the earlier analysis. And helium and hydrogen have retention times that are almost the same.
So it's just the time.
It's just the times. It's the times. And it's funny because it always reminds me of there was a silly little movie that Sean Connery did about, 20 years ago, where he was jumping around in the jungle on these ropes. And he had a gas chromatograph with him. And the gas chromatograph, he ran this, one was a crushed up beetles from inside of a flower. And he ran one, and then he ran another one. It had an extra little peak, and he said, "That's what I'm looking for." And I was like, "How do you know that? How did you know that's what you're looking for? Because it doesn't make any sense." That's the compound. All right.
Anyway, the flux become a common thinking, sometimes we call misconception. That you see really tell you the peak, but really cannot tell you what the peak is.
Nope, it can't.
There is the nitrogen, there is hydrogen, whatever, oxygen. Based on the sample we give, we know this gas air has oxygen and nitrogen.
That's right. The only way that we would know is running an external standard. And in this case, air. We know that there's CO2 in air. We know there's some other things too, we just can't see them because they're below our detection limit. Like there's a little bit of neon in there, and sometimes you can see neon, which also comes around where hydrogen and helium do. But it's very, very small, and it never affects the amount. And I get asked that question a lot. Well, how do you know that's what it is? Well, I look at these columns a lot. It's pretty obvious to me what it is, but it's not to somebody who just walks up and looks at it. So I go through and name it, and in the future, you'll know the elution order. So if things shift, they don't shift out of the elution order. If this changes, like if this column gets wet, these two don't flip. They just all fall forward. So the elution order is the same. There are, and that is got its exceptions to the rule as well. When you get a mole sieve wet, you can flip the CO and the methane. So it's good to know if you get a standard made up of the compounds of interest, get them in different quantities. Don't get a 1% standard of everything. All the peaks are the same height. How do you know the difference? If you do 1% oxygen, 5% nitrogen, 2% methane, you can tell by the area counts which one it is, right? Not just the elution order. Okay, now if I go and look here, because it shouldn't be writing to them, I'm going to associate this with, what can I open this with? I think I can open it with, if you've got Office, oh, you do, good. Yeah, where's, don't have X.
University has a site license with Office, so they're not going to have to
Yeah,
start.
it's not on there yet. You'd have to go through it. Yeah, don't make changes right now. Cancel that. Cancel. So in this case, let's go and do it with, open it with, no, where's open with now? Open with. Browse. Let's just open it with Notepad or something. If I can find something. Messed up by trying to do that. I don't even know where Notepad would be.
It'll be easier to open a notepad than open
Yep. Anything we could always use. Don't always use that. But well, we can open this one anyway with something different. In this case, you're going to want to associate these with Excel anyway. So in this case, let's go with our Word, because Word would at least be a meta file. Oh, watch, it'll come up and say it's not on there either. Let's do WordPad, because I know it exists on there. Okay. This is a lot easier to see when you've got it in a tab delimited form and it's an Excel spreadsheet. But it gives you what you're looking at, which is the report, the channel, the number of records, and the external standard concentration. So right here is the data file on it. That's the date and the time and the method and the external standard concentration for the two gases, or for those two. So the first one did 21.79, 21.69, 21.72, 77.034, and 77.7.8. So when you put it in a table like that, you can take it and graph it, you can run it over time, and you can say, here's where my switch takes place. Might be important to you later. Anything else? Anything? Yeah, the thing that's going to be hard to see on that is going to be, okay, what button did he push? And the only way you learn the software is to learn the software. So we built a method. That's where we'd look at a method. We can look at the data file. We can also open data files offline. There's another version that's offline. And this is how you run it. This is how you analyze it. That's how you calibrate it. But somebody will have to sit here and go through those for it to make sense.
In other words, run analysis
Mm-hmm.
and
Right.
to
And the way that we have it set up, it does the analysis automatically based on what we've calibrated into the analyzer. So you do a run, it automatically does the analysis, so you can look at the report. So it's all finished. This is still pretty messy up in the front. I'll be happy when that goes away.
I think what we do is with this, we will wrap up this session, and after that, I'm going to ask David to help us to install
The
analysis
filters?
filters.
Yeah.
And then at 1 o'clock, Steve Daniel, Dr. Daniel will come also. Most likely we'll not do as formal as this one here.
Okay.
We'll walk and try to interpret. This is a scientist. We want to ask why and do those things here, and how we do it in the future. So we'll take an informal approach and understand the reasons behind. So for example, why do we set at 70 degrees or why do we set at 90 degrees? And there's a big difference in the future. But I guess we'll do a little informal way
Okay.
in the afternoon session.
Sure, that'd be great.
We'll let him drive.
Yeah, one thing we didn't talk about on this, because we were talking about how do you build a method, how do you run a sample, is how does the sample get into the line? Okay, how does that happen? It's obviously carriers flowing through it all the time. It's always flowing through. So how does the injection get into it? And that's easier to draw than it is to say. So from my sheet, I'll leave this with you guys so you can kind of see it, but I break it down really simply. It's more complicated than this, but I break it down pretty simply. If we're taking a sample and it's going through that little 1 mil loop,
and it's going out here to the pump. Each one of these has the same thing in it. So each module has this in it. It's got a little chip injector that's actually smaller than my thumb. So it's my thumbnail rather, it's about that big. The sample, in this case air, is being pulled into here by the suction pump and out the back. And this is set by the sample time in the software in seconds. Once we've reached however many seconds we've got this set for, which is 15 on the right now, this pump shuts off. This is isolated. So the first thing that happens is we close off one end of it so that this comes to atmospheric pressure. Always reproducible atmospheric pressure. Fairly. At that point, we isolate it completely. We isolate this loop. We never inject all of this. This is I think this is 1 mil. We never inject 1 mil of gas into this column. This is a variable volume injection. So how do we accomplish that? There's actually, this is where it comes into play as to what the carrier pressure is. So the carrier pressure's main purpose is to establish what pressure, what flow is going through the column, and it helps set the times and the retention times reproducibly. Sorry. But the other thing in this particular case is it actually helps determine how much of the sample goes online. Because this is isolated, this is at atmospheric, so nothing's going anywhere. I bring the carrier in, and I think, let's go with the mole sieve. I think the carrier's at 22 psi. Right? And it comes into this. So there's a dilution effect. We're bringing argon in, and it's filling up this loop, which is atmospheric, to 22 psi. So if you think about your standard, it's being pushed towards the front, and then there's an equilibration step. It's gas, it equilibrates almost immediately. There's another thing that's set in the software called the inject time. Then we set that in milliseconds. And on this mole sieve, we're doing that for 40 milliseconds. All right, I'll do 2 pictures here. TCD. Now, the flow, while this is set up and running all the time, the flow is coming through here. Constant, 22 psi.
Carrier gas.
Carrier gas. At the time that we make the injection, there's a little solenoid that allows this gas now to come through here and fill this up and equilibrate for, I think it's 40 milliseconds. It doesn't take long. It's preset. And at the end of that time, no, I think it's 200 milliseconds. Then we open this little valve for 40 milliseconds. So at that point, for 40 milliseconds, we let gas come through here, okay, and inject into the column. And then we switch back and we're pushing it through again. So at that point, we're making an injection onto this column. At 22 psi and 40 milliseconds, I think I've calculated this to be 100 nanoliters of gas goes on column. It's not much at all. It's one of the reasons, that's one of 2 reasons why the detection limit is lower and why it's so much faster. The idea behind chromatography is you want to put the sample onto the column as tightly as you can, because then as it separates, it's got it makes sharper peaks. If it's broad when you put it on, then your peaks get broader and it's harder to separate them. So it comes through here, goes through this injector onto this pre-column, which in this case is a pore plot Q. Not to be confused with the other pore plot Q that is the other channel. That's the pre-column for the mole sieve. Why do we use a pore plot Q? Well, if you think about the elution order that I've got over there, on the pore plot Q channel, there's an air peak, then there's a CO2 peak, and then there's a water peak. What hurts a mole sieve? water, and CO2. So what I'm doing is, this is a really short column, it's only 1 meter, and all I want to do is make sure that this peak gets through, but this one doesn't. And in this case, in 8 seconds is long enough for it to go through there, get this peak through, which is my composite peak, oxygen, nitrogen, methane, and CO, and hydrogen in your case, sorry. All gets through, and onto this column to be separated. The other, there's a restrictor here, comes like this. At 8 seconds, this is diverted so that it comes through flowing this way. Now, everything is still flowing this direction for my compounds of interest, which is hydrogen, oxygen, nitrogen, methane, and CO. But still on here is CO2 and water. Right? And it's going to go this way to vent. So we never get these bad compounds onto the whole set. Then these come over here and they separate out to hydrogen, oxygen, nitrogen, methane, CO. And we never see the other compounds. So water doesn't get on here. It doesn't affect the retention time. CO2 doesn't get on here. It doesn't affect the sensitivity. I know it looks kind of busy, but the main thing is this constant determine a reproducible amount of gas. You don't have to know what the reproducible amount is, as long as it's reproducible every time. It's saved in the method. Any change to the method means you need to recalibrate it. If you change what the injection time is, if you change the pressure, the carrier pressure, you need to recalibrate the analyzer, because those two things determine how much sample gets put on column.
This is information I was looking for.
This is information I think that you wanted me to go over later,
Yes.
but at least you got it here too. And there's my handy drawing. I've probably got 4 more of those in here.
This is very critical for us to understand, because
That's the basis of operation.
How do we inject the sample and how much we inject it? That's how-
The critical part is not how much you're injecting. The critical part is that it's reproducible. What makes it reproducible is constant pressure and a set time. It always does the same amount. Any other questions?
If we were to do an injection from a bag, how do you maintain constant pressure?
That's a little bit of an art. You don't push it.
Yeah.
I usually rest my hand on it, just so it's got a positive pressure. If you think about what's happening, if you don't do that, especially looking at oxygen and nitrogen, well, analyzing oxygen and nitrogen is like analyzing for water at the bottom of a pool. We're surrounded by it. So if you don't have any in your sample and you're pulling a vacuum on that line and there's any kind of a leak, it's going to pull it into it, maybe enough to be significant. Where if you have a little bit of pressure on it, it just makes sure that if any gas is leaking anywhere, it's leaking out. Right? So it doesn't interfere with your analysis. The other thing is, I don't think the pump works that well at atmospheric pressures and isobaric pressures as far as reproducing the amount on column, and I think we demonstrated that just a moment ago, because if you go and look, well, it was 100%, now it's 99, now it's 98.6, now it's 99.4. It's a different amount each time, and it's the same amount of gas going on every time, I can tell you.
That's a good point. That helps us to.
What you don't do is put it in a bag and then go.
Yeah.
Okay. Yeah. The whole point is to make sure there's not 15 psi hitting those injectors. For a long time, when we did a standard, the capillaries are very small inside. So for a long time, we didn't think about it being dangerous We just put a septum inject system on here, and we'd inject, and then we'd start seeing problems down the road. You know why? It's hard to gauge with a gas-tight syringe what kind of pressure you're putting on it. And if you're pushing it, there's a restriction going against that capillary. It won't let you push any more than about 15 mils a minute through there. Well, that's pretty small, maybe 30 mils. So you're pushing against it, and the pressure's on the backside. It's not just immediately going to atmospheric on the backside. And people were destroying injectors doing it. So now they put if you get one from us, set up to do injections like we're talking about, it has an injector here. It has two capillaries, or a capillary that comes from this, goes up into a valve. On the back side of that valve is a 7.5 psi pressure relief valve, so that if you do put too much pressure, it pushes it out the back. So you keep a little bit of pressure on it, and then it has two tiny capillaries that come down here and then through the injectors. Generally, with a syringe injection, you can or you cannot, depending on which way you want to work it, use the pump. Some people like to, some people don't. Some people like to just as a timer more than anything else, and they know that it's pulling a sample through with a little bit of pressure.
No, I see the reason, because we contacted them to have the phone call injection and Chuck, the technical support person, contacted the factory.
Right. Would that make it?
No, they said it's not available.
It said it's not available, but I thought they were going to put it together for you.
Is it?
I thought so.
Okay.
I don't know. Maybe I'm wrong. I'll check with
Yeah.
Chuck. I may be thinking of someone else.
Maybe something different. Maybe, yeah, I think that's coming, but.
Let me check with Chuck about that,
Okay.
because that takes somebody coming out and putting it on for you.
No.
And more, people are doing more and more bioreactor and fermentation work and trying to find renewable energy sources. So we're seeing this more and more where they're really limited in the amount that they want to inject. So they want to put a small inject on, and they want to have both capabilities. Well, we ought to make a part number out of it, but it doesn't exist as a part number
Okay.
unless you order it from the factory built that way. Because they don't think you should do it, and they don't think I should do it. But I've done more than one.
That's what we have. We want to train the ability to put a sample into a bag or the inline process, and also be able to do a key.
The best way to illustrate what will happen on that would be actually a two-way valve. So you'll have a tiny capillary coming in the front where the septum is. That tiny capillary will come out to a valve, right? And it can either be this way or this way. On the back side, that'll have that pressure release. Right? And then it will come out of this same fitting down here. In this case, there's a dual fitting here, so maybe a little too small. It'll come back out of this and down into those two splitters that go to the two columns. But they'll also have a line that comes in here. That's your sample line in from the back. So if you switch it, you have the ability to switch and make an injection from the back that then goes through these capillaries, or to close it and go this way and go through this
Right.
capillary.
That's what we want for. We can always,
This option is somewhere around $4,000, I think, if you order on a new one. So we're trying to get them to put together these parts so we can do it economically. We've had it happen more than once. People that get it and assume they can do that, and it's not so. And in fact, on more than one occasion, I think that they were told they could do it by somebody who didn't know what they were talking about. And we're trying to fix them when we can.
Any questions?
Any questions? Okay.
If this is the case,
As I
think
appreciate your interest, if there's anything else I need to answer, please let me know. Another thing you need to remember about the Micro GC, don't put water on it. Don't put any liquids in it. Don't put any particulate matter in it. There are actually two filters on this system. One of them you can see that's on the outside when Bert set it up, which is right here. It's a little 5-micron frit that's exchangeable. So if you see that you're not getting sample in, you might want to check that frit and see if there's anything on it. The other is there's another exact match for that frit, the 5-micron frit, inside this fitting. Don't ever get anything in there because you've got to replace this fitting. That's why we have the external filter on. So that's it in a nutshell.
It looks like it may be, we can do a more detailed training after the video session.
Okay.
For the video session, I would suggest maybe you can do a walk us through the process, build a process, a method.
Method process? Got
Method
it.
building, and then run the method building and run the data analysis.
Okay.
You can use air for
That's what we'll do. We'll run air right now.
Yes.
Okay, so to build a method, the first thing that we need to do is running on experience, which is what I'm going to do. I'm going to guess at what these are. The things that we need to set are going to be the pressure, the temperature, and the length of the run. So the first thing is I'm going to take this little cool down method that we have and save it as something completely different. Let me see if you got one out here first. You have a couple? Is this an air sample method?
I think that's the one, yes, David help us.
Yeah,
We
Bert
can start
did
from
that one, I
scratch.
think. Pardon?
Do one from the scratch.
I will.
Probably the easiest.
Well, it's always just as easy to, I don't think you'll ever have to do a new one, but if you did, you can. It's going to pop up with the same things that are in this cool down. So let's go from the very beginning.
Okay.
Let's back all the way out. We don't care about these.
Right.
So we start from scratch. First thing is we click on this Easy Chrome. And it always opens up with the last thing that you did. I don't like this little screen to pop up, so I'll turn it off and you won't see it again. This is a wizard for creating a sequence, a wizard for creating a method, doing a single run or running a sequence. But everything there's 4 or 5 ways to get to everything in the software. One is through the file menu, where you can open up a method. You can open it up in different areas. You can save methods if you go through here. You can save it there, or you can do a pull down on this icon and save it. I have a tendency to mix up the two, so I'll just do it the way I normally would do. And
Front of the methane, but I like to leave it cool enough so that we can see the methane before we see the CO. CO is kind of an odd little peak in that it has a little bit of a tail to it, and if it's in front of methane, sometimes we can't get a good separation. Now, after that, we're going to back flush it. So the main thing that affects a mole sieve adversely is going to be water. Doesn't like water. Syngas generally has water. It also doesn't like CO2. And the two have 2 different effects on a mole sieve. One is, on a mole sieve, the elution will start, all of the peaks will start shifting forward. That means it's wet. If you start losing sensitivity on everything, that's CO2, and that's harder to get rid of. The main thing we want to do is make sure we get CO2 off of that, keep it off of that, which shouldn't be hard to do at 10%. The other column is specifically, because it's got a little pre-column on there, and we hold up the CO2 just briefly, and then we back flush it to vent. On the pour plot Q, we'll get a composite peak that'll be all of this stuff, except for the methane, which will be separated a little bit. Then we'll get CO2, ethane, ethylene, ethane, if you separate those two, and then you'll get propane, propylene, propane. In between here, you might get a little water peak. So these are the C3s, these are the C2s, this is CO2, and this is C1, or CH4. Okay, so that's the basic principle, is you're doing these.
One more time, because
Sure.
none of us are chemists.
All right,
So,
well, that's okay.
yeah,
Because you don't have to be a chemist, you have to know what the elution order is, and I'm sorry, let me turn that off.
This is super important for us to understand.
Yeah, I mean, it'll be named and they'll be done by retention time, but this should always hold true, because the retention time is going to be set by whatever we set the pressure to be on the column. So we're going to see helium, we're going to see hydrogen, oxygen, nitrogen, then methane and CO. On this other peak, on this other one, we're going to see an air peak, what we're going to call an air peak or a composite peak, that we won't analyze. We probably won't analyze methane. We'll probably do it on the other one. And then we'll start at CO2, C2s, C3s. If there's water, it'll be right in between the two of them. Water is a distinctive peak to
This
see
is
as
for
well.
the DPQ.
This is a mole sieve.
Mosaic.
Yeah. I
This
should
is
have known.
for molecular sieve.
Mole sieve 5A, and this is a porous polymer cube. So that's the basic principle of it.
You can understand that there's more than one way to get there. The first thing we'll do is to tell this instrument what temperature it needs to run at and what pressure it needs to run at, because we need to start getting the temperature up to a level that we can work with. So the first thing I'm going to do is go and do a new method. You shouldn't have to do this very often. And on this new method, I'm going to tell it that the molecular sieve column I want to run at 70 degrees. And I want the inject time to be 40 milliseconds. Something we didn't talk about was what that means and why it's reproducible. There's two constants that make a reproducible injection. One is, and both of them are set in the software. One is the column pressure, the other is the inject time, and I'll tell you why those two combine to make a reproducible injection. My mouse is stuck. Let's open this up a bit. My backflush time, just from my experience, I'm going to set at 8 seconds, because that way it should be cool enough so it won't allow the CO2 to come onto the mole sieve column. We might lose, at this low temperature, we might lose some of the CO, but we'll only have to play with that to find out for sure.
And you are targeting the air analysis.
Air analysis, but I'm going to try to get them all in one. I want to get everything. I want to get hydrogen, oxygen, nitrogen, CO, and methane. So if we can find some methane, we can find out whether this is going to work or not. There's no reason to have multiple methods, because the whole idea is to separate out the compounds and be able to tell based on that what the concentrations are. The detector is on. That just tells me that the filaments are on in the thermal conductivity detector. The TCD limit check is on. All that tells me is that if I shoot a big, huge sample in and it's going over range, it reduces the range to half so that you don't get a big electrical or a temperature shock onto your filament for the TCD. We're going to invert the signal on this one because we're running argon. And if I don't, then all my peaks will be pointing down. I'm going to run in static pressure, and I'm going to put it at 22 psi. This never needs to be messed with. As far as the acquisition channel, I always run a sampling frequency of 100 hertz. I don't know why anybody would ever want to not do that, so I really don't ever change it. The runtime, I'm going to say at 2 minutes at 120.
The Micro GC has two modules in it, or two channels in it. One channel has a molecular sieve, the other has a pore plaque cube, the one that you have. Each one of those channels has an injector. Each one of those has its own column. Obviously the two columns I just named. And each one has its own TCD detector. So what we do is we take the sample and it splits and it runs in both of them in parallel, and then we take that information and then we just do an external standard and say that, okay, based on what our external standard is, here's how much of this product is in this unknown gas that we're going to run. The way that it'll come out, the elution order, and I suppose you have argon carrier and helium. Yeah, right. The reason that we do that is because the thermal conductivity for helium and hydrogen are identical, relatively close to being identical. So you're going to get the same response. If you run helium as a reference gas through a TCD, you won't see anything. Actually, you will for hydrogen. It's kind of an interesting compound. It'll go positive for a little bit, and then it'll go negative. This causes a problem because you never know where the start of the peak is, and everybody's a little hazy on where that crossover point is. I like to think that if you're doing anything lower than 2%, you can probably do it on helium. If you're doing anything above 10%, you could probably do it on helium by inverting the signal. But there's that area, well, maybe 20%. So there's that area in between that it's just an upset baseline. So we run argon because there's great thermal conductivity between argon and helium, and we invert the signal and we get a really nice little sharp peak. What that does for you, though, is it reduces the sensitivity for some of the other compounds. Not that it's going to affect you guys, because the thermal conductivity is relatively close on argon and CO. So instead of seeing like we normally can on helium, we can see about 10 parts per million of CO. With the argon carrier, we'd be lucky to get about 200 parts. Again, well below what you want to see. So the elution order on a mole sieve is going to be hydrogen. Then we're going to see oxygen and nitrogen. And then we'll see either CO or methane. They'll be kind of close together depending on how well that column is separating them or what temperature we run. You can heat it and drive CO in
3 seconds for now, just so I can see everything. It won't be, well, we've only got air, let's just do 60. There's no reason that it'll get everything off in 60 seconds. So that's our first channel, and that's, down here it tells you that this is the one that's running argon, and it is the mole sieve 5A, which is a molecular sieve. The next part, the other channel. It's a pour plot Q. I'm going to run it a little bit hotter at 80 degrees. Again, my inject time I'm going to put at about 40 milliseconds because we should be able to see the atmospheric CO2 when we run this. Detector's on. Detector limit check is on. I'll run pressure of about 18 psi. Acquisition the same, 60-second run so that it matches the other. And that section is built for that particular part of it. At this point, I'm going to save this. File, method, save. And I'm going to save it as the analytical method so that you'll know which one to use in the future. Now I'm going to download this method into that analyzer. The reason I want to do that is because I want to go ahead and start the columns raising up. The thing about chromatography, it doesn't like being turned off. Any chromatograph doesn't like being turned off. You're better off leaving it run all the time. You're going to use maybe 15 mils of gas a minute, milliliters of gas. In that case, that thing ought to last a long, long time, like months. So just leave it running. It doesn't take that much power. Okay, so I saved it. I did two things there. First, I saved the method. I saved it in this method, saved it that way. But I also did something else that's pretty important, and that is that I went to the control section. Everything that's happening on that analyzer right now can be seen through this control section. If I'm going to make an injection, if I'm going to download a method, if I want to check and see what everything is, that's where I go to look at it. So I downloaded the method. When I downloaded the method, it started bringing the temperatures up. And I know this because I can go to the instrument status and look at it, and now my temp is 70 and we're coming up to it. My temperature is 80 and we're coming up to it. We've already hit the pressure points I need. At the end of this time, it's going to come, everything will turn green and it'll be ready to make an injection.
So in other words, when you, I'm sorry.
Go ahead.
After you download the method, that means you literally are running, preparing it.
You're preparing it. You're bringing